7.1 Ratios and Proportions. So this should be a review. I believe that ratios and proportions, you started doing them in earnest probably in 6th or 7th grade math. And our objective in this lesson is to write ratios and solve proportions. Start out with some vocabulary. A ratio is a comparison of two quantities. We are comparing two numbers. So we are comparing the number of boys to the number of students in the class, the number of girls to the number of students in the class, or we could compare the number of girls in the class to the number of boys in the class. And you write a ratio. You can write it in three ways here. You can write it as a fraction and using a colon, and simply as A to B. All of these are read as A compared to B. And we leave out the word compared, but it's A to B. A as it is compared to B. And an important idea here is that A and B have the same unit, and we generally write them in the simplest form, which simply means we reduce our fraction. Even when it's not written in the fraction form, you still reduce it just like a fraction. Divide both of them by 2, divide both of them by 3. So let's look at an example here, writing a ratio. Bonsai trees. A bonsai bald cypress tree is a small version of the full-size tree. So in Florida, there is a bald cypress tree called the Senator that stands 118 feet tall. And our picture over here is kind of hard to see. This is our little bonsai tree, and it stands 15 inches tall. And we want to know the ratio of the height of the bonsai to the height of the Senator. We are told what order it goes in. If you're not told, you can put them in whichever order you like, but that makes it all the more important to make sure you label everything properly so we know what we are comparing. Now, what's the first problem you see here? The first problem I see is that we have feet and inches. So we would like to get them both in the same unit. Generally, it is easiest to change to the smallest unit. So we would change everything to inches. It doesn't matter. If you want it in feet, you can change them both to feet. So let's change our 118 feet into inches. We know that there are 12 inches in 1 foot, so we are going to multiply. We are going to a smaller unit, which means our number gets bigger. So if we multiply 118 by 12, we get 1,416 inches for the Senator. And then we write our ratio as a fraction, and we want our bonsai first, our Senator second. So we put 15 on top and the 1416 on the bottom, and then we're just going to reduce that fraction. Both of these will divide by 3. And we get 5 inches for the height of our bonsai to 472 inches for the height of the Senator. So for every 5 inches of our bonsai tree, there's 472 inches for the Senator. It looks like it's your turn already, so go ahead and pause the video and try the next problem. That was fun. We were told our bonsai tree is 18 inches wide and 2 feet tall, and we want the ratio of the width to the height. So our width is 18 inches, our height is 12 feet. I'm going to put everybody in inches. So I multiplied by 12 and got 24 inches for the height. I'm asked to do width to height, compare width to height. So 18 over 24 and reduce it, and I get 3 inches of width to 4 inches in height. It's a 3 to 4 ratio. We also could have written that as 3 to 4 ratio. All right, that was good. Oh, these problems are good. Ratios are extremely useful. You can use them to do math problems. Ratios and proportions are probably the most useful thing math can have for just everyday life. So we are trying to raise money for our band, and we buy pots of tulips and pots of daffodils. And we are told that we are buying a total of 120 pots of flowers and a ratio of 2 tulips for every 3 daffodils. So this lets us write an equation. We could say we're buying 2 tulips and then we buy 3 daffodils. And that means we would get 5 plants. Right? Well, what if I multiply that by 2? Well, we would get 4 tulips, which would mean we would have 6 daffodils. But that's only 10 plants. Well, what if I multiplied that by 5? We would get 10 tulips and 15 daffodils, but that's still only 25 plants total. Now we could continue on and do this, right? We are just writing, if you notice here, we are writing equivalent fractions. Instead of reducing my fraction, I'm increasing my fraction. Okay, we could just continue on until we end up with some ratio that equals 120, or we can write this. We can find our multiplier. What are we multiplying both numbers by using an equation here. So I know I have a 2 to 3 ratio and I have a multiplier of x. So I'm buying 2x tulips and 3x daffodils, and if I add them together, I get 120 total. So I just do my algebra, and I end up with x is 24. This is my multiplier. This is what I'm multiplying by. It would have taken us a long time to get to 24, wouldn't it? So then I simply substitute in 24 for x, and I'm going to buy 48 tulips and 72 daffodils. I was supposed to be in green. 72 daffodils. And that equals 120 total plants. All right, so it looks like it's your turn again already. Excellent. Pause the video and do the next problem. This problem says we have supplementary angles in a ratio of 1 to 4. So I drew my favorite supplementary angle, which is a linear pair, and I know that one of the angles is 1 times a multiplier, and the other angle is 4 times a multiplier. And I'm going to find out what that multiplier is so that they both equal 180. I make my equation here. I find x is 36. My multiplier is 36. So I multiply 1 by 36 and 4 by 36, and I get 36 degrees and 144 degrees, which nicely add up to 180. That was a fun problem. We're going to go a little farther with this idea. Some vocabulary here. An extended ratio compares 3 or more numbers. So an extended ratio looks like A to B to C. So we are comparing A to B, we are comparing B to C, and we are also comparing A to C. So let's look at a problem using this idea. We are told that the lengths of the sides of a triangle are in an extended ratio of 3 to 5 to 6. And the perimeter, oh good, perimeter deals with lengths of sides, right? Sum of all the sides. Our perimeter is 98 inches. So I draw my triangle, and we could look at this just like we did the daffodils. This side could be 3, this side could be 4, no, 5. And this side could be 6, but that does not add up to 98. So we could do it again, and we could multiply by 2, and we would get 6, 10, and 12. We could multiply by 3, by 10, right? But that's the hard way to do it. We know that we have a multiplier that we multiply all of those, our ratio, by. So we get 3x, 5x, and 6x. Those have to sum to 98. We find that x equals 7, and we simply substitute back in. 3 times x is 21 inches. 5 times 5 times 7 is 35 inches, and 6 times 7 is 42 inches. So this is a triangle with sides in the ratio of 3 to 5 to 6 that has a perimeter of 98 inches. There are many triangles that have this ratio of sides, but they don't have a perimeter of 98. This one would have a perimeter of 14 inches. This one would have a perimeter of 28 inches. All of these triangles have a 3 to 5 to 6 ratio, but only this one has a perimeter of 98 inches. So once again, looks like it's your turn. Pause the video, do the next problem. That was a fun problem. This time our triangle, the sides had a ratio of 4 to 7 to 9 and a perimeter of 60 centimeters. So I just labeled my triangle, put in my extended ratio, put my multiplier on each side, wrote my equation, found x is 3, substituted it back in. Our triangle has sides of 12 centimeters, 21 centimeters, and 27 centimeters. Yay! Okay, let's take this a little bit further. When two ratios are equivalent, we call that a proportion. And a proportion just says that this fraction equals this fraction. These are just equivalent fractions. So if our first fraction is 2/3, what's equivalent to 2/3? 4/6. Right? It's just, you know how to write equivalent fractions. Instead of reducing, you just increase. You can also reduce them. The first and last numbers are called extremes, and the middle numbers are the means. So our means, if we write it in colon form, our means are these middle numbers, and our extremes are the outside numbers. So this is going to mean more to us in future lessons. So your extremes are top left, bottom right. Your means are bottom left, top right. Now, how do you solve a proportion? Do you remember? The cross products property says in a proportion, the product of the extremes equals the product of the means. So what does that mean to us? The product of the extremes, 2 times 6, do that in a different color. 2 times 6 equals 4 times 3. You probably remember this as cross multiply. So you know how to do this. We just now have a fancy property for it, right? Geometry is what lets us do math. And we know that these are equivalent fractions because when we cross multiply, we end up with 12 equals 12. That's a true statement. It means that those are equivalent fractions. All right, how do you solve the proportion? Well, if I'm given my proportion here, I cross multiply, solve for x. Those are easy. 6 times 4 equals 5 times x. Divide both sides by 5, and we either get a fraction, you can turn it into a decimal if you like. Let's look at this problem B here. Uh-oh, what is that on top there? We've got y plus 4. But that's okay because we are not afraid of variables. Right? That y plus 4 is just a number. It's just as good as the 6 that we just used. We are going to cross multiply here. Top times bottom equals top times bottom. But we have to make some special concessions for this number on top here. It is a single idea, right? We are multiplying 3 times the y plus 4. Being a single idea in math means that we put parentheses around it, which means we have 3 times the quantity y plus 4, and then we distribute. So be careful with this. That top number is a single idea, which means you have to use parentheses. And once again, it looks like it's your turn. These are going to be easy problems for you, I know. Go ahead and pause the video and solve the next two. Okay, we have a proportion, and to solve it, we use cross multiply. So 9 times 14 equals 2 times a. Do the math. A is 63. In part B here, cross multiply. It's still a fraction equals a fraction, still a proportion, but we have to be careful here. So we get 15 times n equals 3 times the quantity m plus 1. We distribute, do our math, and we get m equals 1/4, or 0.25, however you'd like to do that. Now I want you to take a look back here at part A for a minute. These are equivalent fractions, okay, right? 9 is to 2 as a is to 14. If you were trying to get common denominators, how do you turn 2 into 14? You multiply by 7. And with a fraction, if you multiply by 7 on the bottom, you multiply by 7 on the top. 9 times 7 is 63. So it shouldn't be any surprise to you that 9 is to 2 as 63 is to 14. You're going to want to do those in your head because they're easy. But I want you to use your cross multiply because when the problems get difficult, like part B, you can't just do that in your head. So I want you to know how to do these properly. All right, let's move on. Ooh, some properties of proportions. These are equivalent forms of proportions. And these three ideas here are going to become very useful to us later on in this chapter. Now we have our original proportion here. A is to B as C is to D. And then what happens? What do? We write the reciprocal of each ratio. The bottom flips up to the top, and the top goes down to the bottom, right? Reciprocal is a flip. I want you to think of a ratio or a proportion. I like to think of it as a foursquare here. And so in this foursquare, we switched the top and bottom on these. Now, does this change anything? When I cross multiply here, I get A times D equals B times C. What happens when I flip them over? I cross multiply and I still get A times D equals B times C. So I haven't changed the problem, I've just changed the position of my parts. But you can see it's still the same problem here. Okay, let's look at the next property. In this one, we switch the means. Which ones are the means? Those are our middle ones. All right, so in our foursquare here, I'm switching these two pieces. Now you might think, hey, that's going to change everything. But here we have A is to B equals C is to D. So when I cross multiply, I get A times D equals B times C. Now in the second one, I switched my means. So the B comes from the bottom left, goes up to the top right. The C comes from the top right, goes down to the bottom left. Say, hey, that might change the problem. But when we cross multiply here, I get A times D equals C times B. Same problem. Now the way I want you to look at this is, what if let's look at this problem if I cut my foursquare like that. I have A over B and C over D. Now when I switch the means, take a look if I cut my foursquare like that. Now I still have A over B and C over D. This foursquare thing is kind of neat because you can rotate it around, you can rotate your numbers around in it and still have a valid proportion. So do you see what we did? We rotated 90 degrees to the right, and A is now over B and C over D just like it was here. So we haven't really changed the problem. And our last one here says in each ratio we can add the denominator to the numerator. Now why does this work? Well, let's look at what we have. We have A is to B, and here we have A plus B is to B. Well, if you remember, you get it with fractions, you get a common denominator, and then you combine your numerators, right? That's the reason we get a common denominator, so we can combine our numerators. Let's separate this back out and turn it into A over B plus B over B. Does that make sense why I can do that? And C over D plus D over D. So here's my original ratio. A is to B and C is to D. And then what's happening here? What is B over B? That's just 1, isn't it? And D over D is just 1. The reason that this works is I am simply adding 1 to both sides. And you know, by the properties of our algebra properties, the addition property of equality says I am allowed to add 1 to both sides of an equation, which is why this one works. And I think that's kind of neat. Math is really neat that way. Okay, so let's look at writing equivalent proportions. In the diagram, we are told that x compares to 6, right? X compares to 6, and y compares to 7. So here's our foursquare. X over 6 equals y over 7. X to 6, y to 7. Now, we want to find out if we compare x to y, what is the ratio of x to y? Well, can you see it? Come back. Can you see it in our foursquare here? What is x to y going to be? It's just going to be 6 to 7, isn't it? Proportions are really awesome. So let's use our properties to do this. So method 1 here says we've got our original x to 6 equals y to 7. And what am I going to do? I want to get y on the bottom over here and 6 on the top over there. I'm going to just switch my means, and I end up with x is to y as 6 is to 7. Or we can multiply. We can cross multiply. And I get 7 times x equals 6 times y. And then I'm going to divide both sides by 7 and get x by itself. And then I'm going to divide both sides by y to get y back here. My y's cancel, my 7's cancel. And I just get x over y equals 6 over 7. So we've seen this now 3 different ways. And the 4 square thing is going to be really useful when we start doing proportions. So our ratio of x to y is 6 to 7. And we are on the last problem here. Do some proportion manipulation, make some equivalent proportions, and I'll see you in a few minutes. In our first problem here, we were given a proportion x is to 6 as y is to 7. And then we were asked to complete the equivalent proportion. So we start out with x is to 6 as y is to 7. And then we were told that 6 is to x as what? Well, what happened here? We took the reciprocal. So if I flip x and 6, I have to flip y and 7 as well. And then the second one, it says what's equivalent to y plus 7 over 7? Well, what rule do we have that does that? That's adding the denominator to the numerator, right? Y plus 7 over 7. So I'm going to do the same thing to the left side, x plus 6 over 6. And then in problem C here, it says explain why 6 over x minus 6 equals 7 over y minus 7 is an equivalent proportion. This is very similar to what we just did up above. We added 1 to both sides. Well, this time I'm adding a negative 1 to both sides, and then I'm taking the reciprocal. So let's look at this. If I do x minus 6 over 6 equals y minus 7 over 7, subtracting 1 and adding 1 are essentially the same thing, right? I'm just subtracting 1 on both sides. That is a perfectly legal move, right? This is just minus 1, minus 6 over 6, minus 7 over 7. I'm subtracting 1 from both sides, and then I'm using the other property, reciprocal property, that says I can put the bottom on the top and the top on the bottom, as long as I do it to both sides. So that's how we end up with this right here. Once again, I feel it's important enough to say ratios and proportions are probably one of the most useful everyday math things that we can use. I use proportions regularly because they're easier to use than a more complicated math equation that would do the same thing. Understanding ratios and proportions especially, will get you really pretty far in life. So I hope you enjoy doing your ratio and proportion problems. Have fun with the homework.